Okay, so let's talk about decoding Morse code and get rid of some of these windows. Morse code, if you haven't heard, is a binary language for humans. It's commonly used for and back in the day, it was used for telegraph. That's what it was invented for. And then it was used again for ham radio enthusiasts when radio became a thing, right around soon after World War II, I guess. And as computers came online, we started using it for, I guess it wasn't, computers had nothing to do with it. So Morse code was never a part of computers, but we're going to make it a part of them. So sailors use it to bang out Morse code for SOS when they're stranded at the bottom of the ocean and they've got nothing but a hammer and they're sunken submarine. So it's a whole alphabet of symbols that just involve those two symbols, dots and dashes. That's why I called it binary. It's not technically binary because the silence is also sort of a symbol because it's an audio signal. You have to have silence signify something. And so these are a series of dots and dashes is for each letter. So we're going to try to decipher a few of those symbols with some Python. So let's load a secret message off of Wikipedia. And this is what it sounds like when you hear it on the radio, or I hope you can hear that. I'll turn it off before it gets too annoying. So that's the message we'll be processing for the rest of the talk, and I'll show you how to work on it. So we need to turn that into data. We need to turn that wave file into numbers. Let me make sure nobody's chatting to me. I feel like I'm talking to myself over here. Make sure that I'm. Can somebody say something just so I know that I'm getting through?
You're getting through. It's sounding
You're
good.
getting through.
Awesome, great. So now we've loaded the file and using SciPy has a package for loading WAV files. There are several other packages for MP3s and whatever else you need. And so we can turn that into numbers. I'm going to do a little math on it because we're not really interested in the fluctuating back and forth. The 255 and 0, that just represents a high pitched beat. And we don't really need 40,000 hertz samples or 4,000 hertz samples. So this 4,000 hertz means that's a 2 kilohertz. Anybody who's a musician will know that's a 2 kilohertz tone that you just heard in those beeps, because it's oscillating between 255 and 0, and that's just the pressure of the air at that rate. That's what you're hearing when you hear sound. Anyway, and we don't need all of those samples. We just need the amplitude of that fluctuation. We need to know how high it is, not how fast it's oscillating. So, what the pitch is, we don't need that. We just need to know whether it's on or off. So I did some processing here just to cut it down to just that, zeros and ones. Is it on or off? And so this is that exact signal you just heard, the first 3 dots, and then a dot and dash, dash, and dot. Kudos to anyone out there who can guess what this letter is and put it in the chat. Dot, dash, dash, dot. Or perhaps an easier one for some people might be the dot, dot, dot at the beginning. So let's try to detect those dots. Let's see if we can write what's called a kernel in a convolutional algorithm convolution sounds like a really complicated word. And I'd love it if you can give me feedback on this explanation that I'm giving about what convolution is. Basically, you take a sequence of numbers, like in this case, I've got these zeros and then ones and then zeros, and you just multiply that by another sequence of numbers like these zeros and ones and zeros. But this one is much shorter, even though it looks bigger than this one. We're just zoomed in on a few of the samples here. So that's going to match up. That is exactly the same width as one of these dots. That's how I designed it. That's why I came up with that 24 ones and then 24 zeros, because that's how long these things are. if you take that short thing and you multiply it by the first bit, it's going to give you some ones and some zeros, and then you sum all those up, and you just keep sliding it across one little bit at a time. You keep moving that little square wave across until it matches up, and whenever it matches up, you get a really big number. Especially if you do what I did here, and that's instead of going from 0 to 1, you go from +1 to -1. So when the negative ones match up, you get a 1. And when the ones match up, you get a 1. It's just when you get a 1 with a -1, when you get a mismatch, that's when the signal goes down. And so if you sum all that up, you end up with a really good algorithm for catching the dots in this case, or the dashes in this case. For a little Python trivia here, you can create longer lists out of short lists simply by multiplying them. It's kind of like and in pathlib, they've overloaded the operator multiplication to not mean mathematical multiplication, but rather mean a list extension multiplication, essentially. And they've overloaded can anybody guess another overload that's happened more recently? Perhaps in another library that's become common for working with files. It's not the multiplication operator, but it's another operator like multiplication, division, addition, subtraction. Does anybody know of another operator that's been overloaded recently to do something cool?
The slash operator in pathlib.
You got it. You're cheating though. You're leading this conversation. You shouldn't be answering the question. I don't think you get to win the raffle. You shouldn't be able to win the Python trivia contest either, because you know all these answers. You probably know more than I do. Anyway, we got we got the dot and dash detecting kernels. That's what they look like again. I plotted them, the actual values of them, because I normalized them because I wanted to use the sum, and I was running into some weird things when I was summing them up. But this is what they look like. You see, I have negative values rather than 0. I have positive values, and that positive value is 1/24th. But just because I had 24 ones, I figured that would work out well with the sum, and it did. So when we slide that across, going one step at a time, just one sample at a time, and go all the way across and multiply it and sum it. This is what you get, the orange symbol. And sure enough, it lines up perfectly where you get a big maximum value when you've found and you matched up with a dot. And it doesn't match up on the dashes. I was kind of pleasantly surprised that it worked. A little unpleasantly surprised that it didn't work on the first dot, because it doesn't have the silence before the dot. So it doesn't really know whether that's a dot or a dash that's ending up right there. So it's going to miss that first dot. So we would not be able to detect, for instance, the character for that. And has anybody put in the chat the answer for the 3 dots and what that might be? No. Somebody asked a question though. Did a human type this audio file out irregularly, or was this computer generated distance? Yeah, this is definitely, it's freakishly uniform. You're right. It was computer generated. So there are all sorts of encoders and decoders. The code, basically libraries that do exactly what I'm doing right now, to detect and also to generate dots and dashes. Okay, so let's see, one last one. So we're going to try to take a dash. And so detecting the dash is just a longer sequence of 24s, and I just multiplied those by 3. So I took the dot kernel and multiplied it by 3. Where is the dash kernel? I moved it somewhere. Here it is. So I just multiplied it by 3, the middle part where there's the ones. So that's all you have to do to create a longer one. And it turns out that's the official. People don't hold down their finger on the key the same amount of time all the time, but the official specification is that the dashes should be 3 times as long as the dots, and that's how I came up with that, and that worked out well with this signal here. Oops, here. The green line shows it detecting dashes and missing on the dots, and so that's what we want. So we could just set a threshold here around 80% probability, and then we'd be able to detect all the dots and dashes. And then once we've got that, then we could do the convolution of that, the dots and dash symbols. That's what this is all about. We're using convolution for natural language processing. So we'd find all the S's, and then we'd find all the O's and find all the S's. So we could find SOS messages and words. You put these in layers in a deep learning neural network. And you don't actually have to hand code all of these patterns. It will learn to recognize them all yourself. And of course, I'm doing this on text. This is out of my area of expertise. I do not know how to do voice processing and speech to text, but I was just having fun trying to come up with a good example to try to explain how convolution works. That's it for me. Anybody have any questions? This did not work out well when I tried to use the S detector to try to catch all the S's in there. There weren't any S's in the symbol to begin with, and I'm not sure why it came out 100 times bigger than it should have. But anyway.
What was the message that it was? I don't know Morse
I never
code, so.
decoded it. It's a secret message, so you'll have to go to Wikipedia and download it yourself and look them all up in the table. I never completed the full alphabet and tried to decode it, but I'm sure it's out there on the internet somewhere.
Any other questions?
Can I get some feedback from somebody on any suggestions for how I could make the explanation better in terms of what convolution is? Does anybody not understand what convolution is and want to ask a question about it?
I didn't understand it at all.
Okay. How could I improve it? Can anybody help me improve it for David? Does anybody understand it? When I said you take this pattern of numbers, zeros and ones, that array of numbers, that list of zeros and ones, and you just go through one at a time, the zeros and ones here, and you multiply the 0 times the 0 or the 0 times the 1 in that sequence, and then you sum up that short sequence of new products that you got. That's what's called the dot product. When you take one array of numbers or vector and you multiply all the individual ones element by element by the others, and then you sum the result up together. That's called a dot product. And that's what convolution is, a bunch of dot products where you just slide that operation across a bigger array, well, a small array across a bigger array. Does that help?
That makes sense. That helps. I mean, I have a math background, so dot products make sense, kind of. I mean, as much as anything makes sense, but like, yeah, convolution didn't exactly make sense. That was helpful. I still don't understand like what does that operation, how does that operation help exactly? I mean, I saw how you were able to like isolate the dots and isolate the dashes, but I don't get how exactly.
Well, it's just that exact math that you just did. You don't get how I decided how to create those, what's called, so the kernel is the small array of numbers, and the signal, the audio file or whatever signal you're trying to process, that's the longer array of numbers. And so, so you just do that operation that you just described, the dot product by the first bit. And so you got this, the first dot product gave me a small value. The next dot product gave me 0.7, 0.7, 0.7. The first few dot products gave me 0.7. And then all of a sudden we started getting some dot products that were giving me some negative or close to 0 values. And then we got some that were giving me, and we went through this, and that gave us the exact position where that dot product was maximum. And so if we were trying this, yeah, you're right. It doesn't really work well when I'm thinking of like a continuous signal like this, because the location doesn't matter when you're doing it on text, but because they're discrete things. But
I think I sort of get it though. Like maybe the right way to explain it is essentially you chopped the audio file up into very small segments, right? And sort of like, if you take, say, I don't know, 100 milliseconds of this audio file, which is only enough for a few, maybe one or two uh,
Dots.
dots or dashes, right? If you take the signal that came out of the audio file and you sort of describe that the signal in the audio file is either 0 or 255, so you have this 100 milliseconds essentially array of zeros or 255s, and then you've taken a dot product there to try to determine, is this a dot, or if it's long enough, is this a dash, or is this a silence, right?
Exactly. And you can create these patterns for much more complicated things than dots and dashes too. So that's the real power of them. When you're using them not just for on and off, but you're using them for the tone of your voice when you're speaking something. So these convolutions are also used to detect the phones, they're called, the parts of words that you're speaking, the sounds that are coming out of your mouth.
Got it. Yeah, some of this, I mean, maybe I'm just putting it together more slowly than people who work on this on a regular basis, but yeah, maybe just describing how you sliced up the audio file and then converted that into sort of like an array of numbers based on, you know, was it loud or was it quiet in this case? But like you could have middle ground between 0 and 255, obviously, if you were doing something more complicated than Morse code.
You got it.
Got
Yeah,
it.
so I'll chop it up. That's a really good suggestion. Anybody else have some ideas or thoughts or feedback?
Hobson, I can't get past the lecture that I had for like, I don't know, this was a long time ago. I think it was linear algebra, and I'm seeing matrices in my head and I can't get past, like, I get that you're graphing them, but like, how does the dot product translate onto that slide? Would that be, I mean,
How does the dot product translate onto what?
I mean, so the ones and zeros, right? So it wasn't put in a, like in my mind, I'm thinking like, it wasn't put in a matrix. So is that related at all? Because that's where I know dot product from.
Like if you yeah, the multiplication and the sum, that's what dot product operation is. Like if you have three numbers, a three-dimensional vector by another three-dimensional vector, you take that dot product, you're just multiplying the first one by the first one, the second one by the second one, the third one by the third one.
Yeah.
And then you're summing them up. That's what a dot product, that's what the math of dot product means. So when you put a dot, a big black dot between two vectors, that's what you mean for the person to do to get a number out.
So I think the reason why I'm confused, like I didn't see like a matrix in the beginning in order for it to translate into, you know what I mean?
Yeah. Okay. Great. Yeah.
There
So
was
I need to.
something in the beginning like that. It would kind of help people remember.
Yeah. Yeah. Okay. Great. Yeah. So I'll show the square brackets around a sequence of numbers, and I'll put the horizontal and vertical so that they understand what I mean when I'm saying a dot product. It'll. Okay. Got it.
I think that would definitely help. Like if you talk about how you sliced it up and then you show, okay, so if I take this 50 milliseconds or 100 milliseconds, now I have this array of numbers, and you could show the vector and say, okay, basically if this vector is this value, it's going to be, if the dot product of this vector and I don't know, whatever the other vector is this value, it's going to be a silence. If it's this value, it's going to be a dot. If it's this value, it's going to be a dash, right? Something like that. Although I guess the dots are different time lengths, so that's a little bit confusing. But anyway, I think something like that could work.
Hey, Hobson, another thing that you could do is in the deep learning courses on Coursera, Andrew Ng has some like videos where he explains the convolutional neural networks really well, and he goes like slide by slide. I'm not saying that you should, steal his intellectual property, but you could look at the visual demonstrations and look at his explanations in those courses, because that's how I learned about CNNs. And I think that'd be very useful because it goes like side by side. It's like, okay, we applied this convolution and now the shape looks like this. And you could apply it to images, but then you could apply it to sound waves.
Right, right. Yeah, Leo has been kind of pushing me away from audio, and I've been trying to get away from images because everybody's done the image convolution. But yeah, you're right. Andrew Ng does do a pretty good job of that, at least for the visual world. It's a little easier when you're talking about masking, and I think Leo has come up with a really good explanation that we're working on involving masking. It's kind of like stenciling. So the one here's how we've come up with it, because we're actually doing it on text. We're gonna talk about how. Does anybody know what a stencil is? Where you have a bunch of letters that are cut out of a piece of plastic or cardboard. Well, if you have a bunch of those cutouts in of letters, and you paste all the letters together for a word, like say sacred is the word that we're going to use in the book. So we have this word sacred and cut out of a piece of cardboard, and then if it's the exact same font size as the printed word in the book, you can slide that across, and then when it matches up with sacred, it gets you get the hit of everything turning black, and so you know you've got a match, and so you're just sliding that over one letter at a time to see when it matches. And that's what convolution is doing. It's increasing the signal when some sort of a pattern matches up between the stencil, which is the kernel, and the background signal, which is your input data.
Do you see convolutions being used in video-based recognition? Just adding on that 2 dimensions.
They're used for things they really shouldn't even be used for, and they're used in ways that they're not really intended because GPUs are so good at doing them, because they are just dot products, and GPUs were designed to do dot products for video games, to be able to just multiply the 3-dimensional vectors for objects in the world, so they know where they all are and keep track of everything for 3D worlds, or just graphic render, just shrinking images and expanding images, all that stuff. All those operations require dot products, and so yes, they're used all over the place in video and 3D animation, and convolution is a part of that. Convolution is just a pattern recognizer. You put the pattern into a small matrix or array, and then you try to find that. You just multiply that by a bunch of other numbers somewhere else and try to find that pattern somewhere else. That's all convolution is all about. So it's useful for anytime you want to try to find patterns.
I see it's used in evenly spaced data, but I was wondering, is it going to be used something like in a JSON blob or something?
It's you can use other algorithms, but you got to first sync them up to the same sample rate, so that JSON blobs. I mean, but those are still characters, and those are still discrete elements. So you could find, you could do NLP basically on those characters. You can do convolution on those characters, but when you're talking like audio, like if those dots were 2 times as long or 3 times as long, this convolution wouldn't work. And so you've got to do what's called time warping to compress the time to get to some standard time. There's all sorts of math that you can do to figure out, okay, what is the right squashing I need to do so that these 2 things get closest to each other as possible. You stretch your kernel or you compress the signal. It's like speeding, on your audio file, you can speed it up and slow it down. You do the same thing on your kernel. You just do it, you warp it. So you speed it up a little bit, and then sometimes you slow it down, you speed it up and slow it down, depending on who's speaking or what's going on. And all that math is involving convolution and dot products back behind the scenes.